here. Can we just go back? See, the set of all the histories is 4. There are
Yes.
4 possible histories.
Yes. I'm
And
now
what's the size
constructing
for
the power set of that. The set of all
Okay.
subsets of.
Fine. Yes, so start with the empty set, and then
The first set line is a set gamma 1, gamma 2, gamma 3, gamma 4. They're the
So,
fine grained.
what's confusing me is that this gamma notation looks like it's only one segment, not
No.
the entire
No. So that was Radhika's question as well. But basically, it's this entire thing.
It's gamma 1, okay.
So it's the finest grained history. That's why I put it down in this way and said gamma 1 and gamma 2, for example, are the right two paths that go to the right. And so I'm partitioning it in different ways and suggesting that the different partitions give you different questions, which you can ask: does this happen again?
Yeah. Okay. Now this diagram is still not
Okay.
completely.
So then 1, 2, 3, 4, and then here's the thing: well, this set gamma 1, gamma 2, which is the right movers here, and then.
So that, when you write 1, that's the, strictly speaking, the singleton set, the set that contains only gamma 1.
Yes.
It's not gamma 1 itself. It's not.
No, it's not gamma. It's just that set. It's just if you want to.
Yes.
Yeah, I'm not putting the brackets
Right.
around that.
Yes.
So it's just a
1,
set.
2 means
1, 2 means.
gamma 1 union gamma 2? Or
Yes.
okay.
Yes.
1, 2 is gamma 1 union gamma 2. So this set here in yellow, the right set.
I mean,
Okay, I think in 1, 4 you joined 1 and 3 rather than.
No, that's 1 and 4. Okay,
The
sorry.
set 1, 4 should be joined. 1 should be joined to.
Sorry,
that
this
line.
was a mistake. Okay, 1, 4. It's very messy, especially I should have done a lower.
yeah, if you did 1,
If I just did, okay, let me just do the 3 case to.
it's always a cube. It's always a cube of some dimension standing at its corners.
So this, and then this of course,
Two to
so
the
let me
end.
just
Yes,
finish
it
this
is.
and say that what you have here then is omega. So this is often called a Boolean lattice.
Our set means the set of all sets.
Lattice because it's a coset, so ordered by set inclusion. Okay, so it goes up. This is a structure which I find very useful to think about, especially when we start to talk about cosines. Okay. So if you just had 3, this is clear. Of course, you can do it completely. This is 1, 2, 1, 3, 2, 3, and 1, 2, 3. Yeah, is this clear at least?
Now, what is the physical significance of all this?
Okay, this is, in this case, the set of questions you're going to ask.
So basically,
all of
ones
these-
higher include the ones lower in the
Yes.
hierarchy.
So
It's
there's a,
hierarchical
that's
structure.
right. So there's a set inclusion that is there. So this means, this line here means this is above this, means that this is larger than this, strictly larger than this.
Has more elements. in it.
Yes.
Yeah. Okay.
This is a subset of this, however you want to, in this.
There's a binomial expansion subset.
Yes, it's absolutely. In fact, here you go. 4, 6, 4. 1, 4, 6. Alright, and here you get 1, 3. So that's how you construct this Boolean lattice. So why it's useful is that in all the finite. Pardon?
Is 1 plus 1 to the power n.
Yes.
That's why you get the binomial
So-
expansion.
Okay, so I'm not. I'll finish in an hour. All right. So what is so? This is just this at the level of the event algebra. This is the structure, and for now we won't worry about the infinite case. But that is, of course, something that one is interested in. And so I'll just say a few words, saying that in the infinite case, what you want to. Okay, so I'll say that in a bit, because I first want to say something about the measure, because now we say that, well, mu takes A into, this is the probability measure, right? For everything it's going to tell me what the probability is, and
We're still classical.
I'm just describing the random walk so that then we can generalize to the quantum case. And you see why this is, to me at least, this is very appealing, because the generalization is in some sense completely straightforward. And I mean, not to say that the interpretation is so easy or anything, but the generalization in a mathematical sense is very straightforward, much easier than Hilbert spaces and non-commuting operators and so on and so forth. Okay? And So I have probabilities that I can give to these various things, like I can say, well, the probability for return is going to be half, right, in this 2 times step thing. The probability to go right is again half, and so on and so forth. So I can just assign probabilities for each of these. So of course subtleties arise when I have...
These you just assign by hand, no?
Yeah, okay, so if it was, I'm saying mu is an unbiased random walk. If it was a biased random walk, I'd get a different number. So for every mu, I have a different dynamics. I have a different set of answers to my questions. Yeah. Of course, how I interpret those answers, I'll come to in a bit. I will say, so this point that you were asking about the generators, in the infinite case, so the reason I need the measure is because in the finite case, I have a meaningful way in which I assign measures. It's an unbiased random walk. I say this is equal probability to do this, equal probability to do this, and so on, and I can construct, or if it's a biased one, I can still do that. So I have for every finite path, I have a probability. Right? Now, if I think of the infinite time path, let's say that I stick to gamma 1. I can stick to gamma 1 up to time t2, but then after that allow it to be anything. Okay, up to time t goes to infinity, I can allow it to be anything. And that object, okay, so let me just say, so in that, so it looks something like this. It looks like something which is sort of anything in the future, any particular path in the future, the set of all those paths, an infinite number of them, right? But to that set, I have to assign a measure, and I'm going to assign the measure that I've associated with this finite time path. Okay? That's what I will, this set which I generate from this finite time path is what I'm going to call a cylinder set, and that you can use to then generate the rest of the I mean, you go finer and finer as you specify more and more about the path. And in this particular case, it has a very, what is the word? A very definite structure to it. Okay? But that is how you would generate the sets. So I'm trying to not say anything about the algebra at the moment, because we'll say something about it when we talk about coherence.
Could you repeat that again? Just up to that, up to 2 you go and then you get all the paths from there. And then you take the
So then what is the probability you want to give to an infinite time path? If I think about it, any given path which runs for infinite time, you would think that, okay, the probability of a single path is going to be 0. So how do I can't start by giving probabilities to the fine-grained histories, because then I would come up with something meaningless. It's like if I take a line on this, if I take a line into, and I try to put a measure on it by putting a measure on every point. That's not how I construct a measure. Because if I did, then every point would have 0 measure, and then I would basically not be able to get anything meaningful. So the only way to put a measure on this is to construct this event algebra, or this set, this measurable sets on this, which are going to be now the intervals, open intervals on the set, for example, and to then assign to each of them a number. Okay? So this is what a probability measure, this is how you would define a measure on this, or a measure on this line, on this interval. It's the same way that you can't start off with the infinite time path, because you know the probability measure on that is going to be 0. Okay, so I'm just going to look at discrete time paths which are finite, so I don't run into any confusions.
Just a small question.
Yeah.
The reason I was asking is that if you contrast with classical stochastic mechanics, then probably it's more similar. But if we go back to yesterday's thing about classical determinism and what are the kind of questions you just said you can ask and not ask. So classical theory with the point particle, the sort of questions I can ask is what is the position at any time, right? At all times. I want to know. I can ask an infinite set of questions and get one trajectory out. Right? That's the whole distinction between classical mechanics and whereas now
So here classical
Here you're
mechanics
saying
would be
certain kind of questions are again not to be asked, right?
no,
You
I'm
can't
not saying
ask
that. In
all-
fact, I'm saying all of that. If I had a, or you're saying if I have the infinite time path, I'm saying that
yeah,
it's
so
not.
classical say I have
But
just
if I had,
quantum
so
particle mechanics, I can
yeah,
classically
so
ask
let
for
me
the
just
finest.
answer. Yeah, so let me just answer that because it's a very simple, at least I think a very simple answer to that, which is that in that specific case, when you're going from a stochastic theory to a deterministic theory, you're putting a measure which is a very singular measure. You're putting it all onto one history. So you don't encounter this issue of zero probabilities for, if you had to distribute it over an infinite number of histories, then of course the probability would be zero. So if you put a singular measure on it, and that's a specific example of a stochastic theory where you have a singular measure. It's completely peaked on one, it's zero everywhere else, but it's one on this one history. Then you have everything.
Yeah.
Does a particle go through there? No, it
I
doesn't.
understand. I'm just saying that by virtue of the setup, we are not allowing certain.
No, I'm not
maybe
allowing
I
it.
could say something here.
Sure, okay, Megha.
This is all technicalities in some sense. I don't think that anything of physical importance is here, but you never know. Sometimes technicalities, physically
Like
important
you.
things masquerade as technicalities. But if we address this, then if you use the sigma algebra that people would normally use, the one that's generated by the cylinder sets that Sumati just defined, you would find that any question you can think of is in the sigma algebra. Nevertheless, there are in principle questions that you could ask, not in practice, but in theory, that would not be in the sigma algebra. But to actually come up with one of those questions, you need to invoke the axiom of choice. And in fact, if you deny the axiom of choice, then you can't even prove that such questions exist. So these other questions that you cannot ask are called the non-measurable sets. And whether or not every set is measurable hinges on whether you accept the axiom of choice or some alternative axiom. So what that means in practice is that you'll never think of a concrete question that would not be measurable. So in practice, you would be able to ask every question that you could ever express explicitly, and that would be enough actually there's enough such questions to pick out uniquely any given trajectory that you're interested in. Because you could just ask the question, where was it at time 0, or was it at time 1, where was it at time 2? And given the set of all, ensemble of answers to all of those questions, that would pick out a unique trajectory. So if you ask, is it this particular trajectory which just oscillates 1, 0, 1, 0? That is a measurable question. It is a measurable set. So the singleton sets are measurable. But as somebody said, they have measure 0.
So that's fine. That they have measure 0 is okay, but that
But he's
they are
saying then
measurable
that you
sets
will not
is
therefore be
really
able to
but it's
describe
okay.
a classical deterministic system strictly within this framework. I'm telling you
I'm
that
thinking
if,
of the unbiased random walk. when I
Okay.
said it was
But that's
measure
okay,
0.
yeah. So
But in
then
any
in that
case-
case, I have no question. So we can continue. Because it's just-
Yeah, it's another confusion. My understanding was that, say, if I am doing probability theory on a phase space, then you can define the sigma algebra by using a measure, but then you have functions which map the space into complex numbers. Using the Lebesgue measure, we can integrate the function and get the mean value. So I thought that at least the phase space picture, all the measurable, what the numbers we get are mean values of functions. Likewise, when we do functional integral, we get mean values of operators or maybe trajectory, whatever it is. Maybe objects which are localized in some space-time region, whatever it is. But here it appears to be the dual picture. I am a bit confused. Where are the functions? This appears to be directly saying that the space itself can be measured.
yes, so
But
space of
that is not what
history
is
is,
done in classical mechanics.
No, I'm
it
not
is-
sure why not.
why this
That's
is,
not what is normally done, no?
this is classical stochastic theory. This you agree that this is how you do classical stochastic theory? I mean, if I was to
There's
do
some
the
duality,
random
what
walk,
I
or if I
learned.
was to do Brownian motion, any of these things, because if the Brownian motion is a continuous case and so on, so I have to be much more careful how I define these sets. and one would encounter the issue of fine-grained histories not being measurable.
But they
But
are,
otherwise
they
we-
usually are measurable. Normally they are measurable.
For example, if I write x of t,
But
x is a mapping from the real line to real numbers. Right? So I am looking at,
no, but you're quite right. There's two dual ways of defining a measure. You can define the measure in the way Sumiti is doing, which is, I think, the more direct. I think it corresponds more to the underlying idea. But the two are dual. You can also define a measure as a linear functional that takes, which is the integration operation. So as an operation that takes functions on the sample space to complex numbers.
but they one
And
can
those
get
are
from the-
those are dual formulations.
Yes, one can get
But
one
they're
from
the
the
same, you
other.
can get one from the other. So.
From Lebesgue integration is done in fact that way, no? Not the remote.
So I'm not understanding
People
Paul. I
set
have
it up in
to.
different ways.
Huh?
If you look, I mean, people set things up in different ways.
Okay.
But if you read Kolmogorov spoke on measure theory, it's done exactly this way.
But
I mean,
what
at
is
least
confusing
do or
is
anybody will do.
that when we do functional integral, for example, okay, I don't measure the probability of a path. I look at functional integral provides a way of computing expectation values, but that is not the view taken here. So there appears to
So
be
here we're
a-
taking an expectation value of a step function, if you like, or a characteristic function. So
You define the set and then it's either there or it's not there.
define the function, which is one. Say your set was, what did you call it? Return or something. That's a particular subset. It's a particular event. So it's a subset of the sample space, of the history space. So imagine the function which is 1 on that subset and 0 everywhere else. Then its expectation value is the measure of that event.
But then these functions have a natural algebraic structure. For example, pointers multiplication.
Yes, they do.
What is the structure you are putting on the functions?
It's this algebra. It's
But
a,
there
it's
is a
dual.
dual-
It's a dual expression of the fact that this is a Boolean
Is
algebra.
it, it's not,
If you
it's something like the probability distribution versus the generating function, that kind of duality. isn't
Huh?
it?
Yes,
Is it something-
yes, it's very much that kind of.
No, the algebra
See,
is.
But if you want to make the algebra strictly isomorphic, then you should use Z2 valued functions. rather
But
than-
that is not the algebra we normally put. But
No, so it's an algebra.
So where is
derived-
that
so it's
algebra?
well, it's some new algebra derived. It's the algebra. It's L2 of the omega, or it's L1 of omega, or whatever.
You could take
Whatever algebra.
any function and expand it in terms of these characteristic functions,
Yeah, exactly.
like the Fourier idea.
That's what I'm saying, the
That would be
generating
one way of
function
relating
is what
But where is-
the characteristic.
normally we have these functions from phase, say, say we take functions from the algebra, from the manifold, and on the functions we can put non-commutative algebra.
Yes, if you, yeah, but before you
They are
do
not
that,
doing that algebra at all.
no, before you make it non-commutative,
You have a sigma algebra on the base. Yes.
no, you can take a function and expand it in a set of
I
characteristic
would like
functions.
to have this conversation. I mean, I'd
Okay,
like
maybe
to
we should
understand in
continue.
more detail, Bal. So can we? I mean, I'd like to understand your question better, but I think that it'll take me a long time to understand it. So, no, but so I'm not understanding it because even this particular analogy with generating functions, I'm completely missing. So anyway, so let me just tell you what the quantum measure is. Rafael said something about it. Now we know what rules a classical probability measure satisfies. We know it satisfies additivity. So you have A and B, which are disjoint sets. Then the probability of A union B will be just the probability of A plus the probability of B. And we know this is not true in quantum theory. So in a sense, we know that this is the definition. We knew for a very long time that this was not the definition of the quantum measure. This is not the definition. The quantum measure in general would violate this. Oh, until Rafael came up with this expression here, I think this is sort of a negative statement. The question is, what does a quantum measure satisfy? If you're going to think in terms of a measure theoretic structure, what does it satisfy? And it turns out that ordinary quantum mechanics satisfies this sum rule, and in fact, which is the Born rule and so on. and which is what Bushi tested with a 3-slit experiment. And so you have, in some sense, a positive statement. The quantum measure is 1.
You left out, you haven't finished.
Oh, sorry, I forgot because I got distracted by the generating
So,
functions.
yeah, C is an empty set and
Yeah.
No, yeah, sorry. Yeah.
But now, after learning
I
from
thought it
them,
was really efficient by putting everything down. But,
I always include the dark tones.
Yeah,
but-
music.
Huh?
In experiments you have an A.
One
Yeah,
more thing.
I'll just
One more
leave
time.
that out. No? So I just want to be as complete as I can be in this. So there is this new rule for understanding what this new kind of measure is, which is that it is one that satisfies this particular condition. So Sorkin so Rafael has this beautiful hierarchy of measure theories, starting off with the classical measure. Then you have the quantum measure, which satisfies this condition. And basically, this is a condition that says that I3, the interference between 3 of these is 0. Okay? And so, where I3 is basically just take everything on the left-hand side, and that's it. Okay?
So I'd like to just point out here, so I3 is not necessarily, it's not the triple slit interference, because people get confused. You do have a triple slit interference pattern. I3 is just the extra contribution which might come if you have triples of paths.
Right, so I2 is what you would expect. I2 are the two-way interference terms, which we
That's
know
right.
happen in quantum mechanics.
Yeah.
I3 are things that would happen if it had some more, actually nature obeyed some other more general rule.
If there's
Okay.
a cubic.
And if this is 0, then we have our standard quantum mechanics, which is this is not equal to 0, because this, again, now is going to just be given by this with everything on the left-hand side. And when it's 0, we're back to classical measure. So there's an entire hierarchy. I won't say too much about it.
This looks like a cohomology statement, no?
Cohomology,
Yes.
so I'll have to take down everything
Delta
you
mu.
say.
It seems that some sort of cohomology is lurking there. I think.
Delta mu of A, B, C is
Yeah,
0.
yeah, it has the flavor of cohomology. And in fact, who was
X3,
it?
yes, 3 of
Chrysos
Yes.
Malakos and someone
Huh?
else.
hook shield.
And Unam sort of worked out quite a lot of the formal structure of this. But I don't know exactly how it
So when you
works.
have non-trivial cycles with IN is not 0, right? Right? I mean something like that, yes.
Counting this, checking for holes.
Holes in the...
Yes, they did. They worked out the mathematics of
Who
it.
did this?
Chrysos Malakos.
Okay.
His name is the same word repeated 3 times. Well, at least twice.
So there is, yeah, so I mean,
Chrysomalakos.
so there is this beautiful structure,
He
this...
did the work with someone else, I can't
Someone else,
remember.
okay.
It was in Mexico City also.
Okay. So what I want to say is that...
you need to have A, B and B at disjoint,
Also.
right?
Yeah.
In that, I mean, you need to have that also.
Well, in this, so in the simplest version of it, but you can of course now generalize it to non-disjoint things. But let's sort of see what this I2.
I think when that union there is sort of square, that's meant to,
This is the
So to
square.
go to the
This is what
next,
I mean
yeah.
by disjoint.
that's meant to imply that they're disjoint.
So this is meant to be a square. You can generalize it, and so there's a nice little algebra you can do with these things. I'll just say a few words about this. So,
Just
yeah.
summarize and clarify. So quantum measure is just a positive number for each event, which
Yes.
which satisfies that relation.
Yes.
That's about.
So that's right. So this positivity is important. And so what is it? But then of course you have this way of writing the. Okay, let me just see what I should do quickly. So of course I know that this I2 of AB is just this. interference term that I have. And let's just ask, what are the properties of this interference term? It is real, and this is where that discussion on real and complex comes in. Okay, the real and Rafael, someone asked, why do complex numbers come into quantum mechanics? And really, if you just stayed with this at this level, it's mysterious why they come in, but so we have to actually put in some more information or put in more generality than is suggested by these relations. It's symmetric, so I2, AB. Okay, so there's symmetry. It's bi-additive, and this follows by, actually you can sort of use this, an expression for I3 to show that this is in fact true, that I2, and this is algebra that will just take me a little time, but it's very easy to follow. If you look at, by the way, so like I said, I'll put up the references right at the end on a slide, so if anyone wants to pursue these. So it's bi-additive on both of these report. Okay, so I can now extend to, I've only talked about disjoint set so far, but I can actually write the quantum measure, which I've sort of written as a separate object here, apart from I2, but write it in terms of I2. If I simply extended it, use these properties and extended it to sets which are not disjoint. So in particular, if I just, so I look at,
Sumati, these are consequences of that, or these are extra relations?
So these are not extra relations. This is a consequence of positivity of the measure.
Yeah, and
Yeah.
that.
And this I3 being equal to 0. So things that I've missed out saying. So there's a whole algebraic, lots of relations, very nice relations. One important thing is that if n is equal to 0, some nth order interference term is equal to 0, then all higher ones are also 0. And using that, you can always express higher order ones in terms of lower order ones in a specific way. And that's how you get the additivity, bi-additivity. Okay? So there's a very nice structure to this whole set of, this whole class of generalized measures. I just don't have time to go through the details. So
H bar is not appeared anywhere
Huh?
About quantum measure, there's no H bar in anything you said. Yeah.
I mean, it will come in, of course, if I put in a value to that, and I put E, if I say that the amplitude that it's coming from is e to the I s of gamma, and then of course, so I'm not sure how much I can do. Obviously.
I not ask, I can ask
Huh?
later. Maybe I'm delivering.
No, because I just realized I want to also say something about the decurrence function as well as, okay, I'll just rush through it. Okay, so let me just, the reason being that I feel that there's this level of structure which is there is, like I said, there are lots of open questions, but what I wanted to convey is to convey the level of structure that is there and the level of similarity with things that you already know in classical stochastic theory. So importantly here, so the only reason to bring this about is because you've got a new definition, new kind of measure. This is the definition of the measure, but it has these properties. And you can basically extend it using bi-additivity. If you just took bi-additivity for the case of, if you just took A union B, then you can see that just using the bi-additivity rule that basically I2, so I'll write this here, I2 of A is equal to twice of the measure. And I'm going to use interchangeably mu of A is the same as A and so on. Sometimes it's easier to use that. Okay? So I can actually now think of the interference term as also really being the measure, but it has this property of being real. And we know, or we have the experience in quantum mechanics to say that, well, really there are complex numbers.